So yeah, thank you very much for having me. Hello. So the first thing, I should say this is joint with my advisor, Jeff Kahn. So everything is with him. And yes, I'll be talking about cover time of random walks on graphs. So the setting G is always going to be a finite simple graph on vertex set V. And vertex set is always going to have n vertices. And so sometimes V will also be state space of a Markov chain as well. So I'll probably forget to say that when we get there. Okay, and a random walk on G is a sequence of vertices. So these are random variables. And we have that these are vertices. And then also it's going to be a simple random walk. So xi plus 1 is uniform from the neighborhood of xi. Okay, so yeah, I'm not going to talk about this beyond right now, but some people care about what the starting vertex is. But for us, it's just arbitrary or your favorite starting vertex. And the term that we're studying is tau. So this is the cover time. And it's the first time that all vertices have been visited by the random walk. Okay. So yeah, this is the full setting. All right, so just to get a quick idea of this parameter, we'll set G is the complete graph. And we'll define V is, so actually let's just, so expected cover time in this case. Actually, asymptotic to n log n, and this is a coupon collector argument. So relatively standard, and it turns out it's somewhat extreme. So to get an idea of the expectation of this random variable, we have the following result through the FIGA from 95, and it says for any graph, expected cover time is at least n log n. Okay, so actually it turns out this little of one term is necessary. So there are examples with slightly smaller cover times in the complete graph. But there, morally the truth is complete graph is somewhat extreme, and really the little of one term depends on the starting vertex. So it might be for the worst case starting vertex that the complete graph is actually extremal. And just to mention a quick conjecture here to support or maybe suggest this is that if G is regular, then it seems that the cover time of G should be bigger than the cover time. Okay, but
I don't know if you mentioned about if for people who never seen cover times, there's always a polynomial bound. Right, you're going to talk about this.
Yeah, I wasn't going to mention this, but yeah, probably good to say.
It should be, yeah.
Yeah,
it's polynomial for any graph on n vertices, it's like n cubed at most. And for regular graphs, I think Mike Sachs showed that it's
n squared.
N squared.
Yeah.
Yeah. So it's small, but
yeah. And I should even say like FIGA proved the upper bound for the expected cover time as well, and has the asymptotic term, the leading order term. But I think the exact result also might be unknown for this. Oh, actually, I think Winkler and maybe Brightwell have found the exact upper bounds. So they're slightly easier. But yeah, everything is polynomial. But today, we're going to be studying a different regime. So we'll fix some constant C, and we want to know probability that we cover in a linear number of steps. So here, things are slightly different. And let's just work on the complete graph again here. So for G is a complete graph. Now we'll take Z is number of missing vertices. After CN steps. Okay. Okay, so we can write Z as the sum of some indicator random variables that B is missing. So we immediately find the expectation of Z is really equal to n times probability some vertex is missing. And let's quickly do this. And then we'll really think about this as n times e to the minus c. Okay, so we in the complete graph, we expect that a linear number of vertices are missing after a linear number of steps, and moreover, Z is concentrated. So you can look at like the Dubroff martingale of Z, and this has bounded differences. So we get something like probability that we cover in linear time is equal to the probability equals 0, and this is exponentially small. So yeah, sort of the motivating example. And I should say, in a lot of cases, we think that the complete graph has the lowest cover time among all graphs. So somewhat natural to conjecture, and Benjamini did this in 2009, which is that for any C, we can find an epsilon, and this is independent of a graph, of which graph we're on. So that for any graph, the probability that we cover in linear time is exponentially small. Okay, so yeah, so we just showed it or sketched it for the complete graph. And similar cases, if you look at like the path on n vertices, the result follows from like Hofting or Chernoff bounds. And really, same argument goes for anything that looks like a path. So if you have some linear number of vertices arranged in some way, which maybe rough isometric to a path. So you get this, and you might think, just looking at it, that there would be a simple argument using martingales with bounded differences and applying the Azuma-Hofting inequality. But somehow it's not so clear how to make this naive argument work. So for example, with this martingale Z, the number of missing vertices after Cn steps, the Dubroff martingale of this can have large differences. So we can't show a bound on large differences. The cases in which differences are large, it seems a bit pathological and seems like a very special case, but yeah, it's unclear how to make this martingale argument work. So for previous work,
maybe you want to push the bottom board up, and then it will be seen both by people watching the video later.
this could be quite complicated. Yeah, it will take me a few years to figure it out. Okay. Yeah, so we have the result for a few special cases. You apply standard results, but Itai Benjamini, Gorelgorevich, and Ben Morris. 2010 gave some evidence for the conjecture in the case of bounded degree graphs. So here, for C, the number of steps, and D, a bound on the max degree, there exists some epsilon such that if the max degree G most D, then you get the linear cover time statement. Okay, so they proved for bounded degree graphs, and then 2 years later, Yehudayev shows it for trees. And he also points out that the case of expanders, meaning some eigenvalue gap, is contained in the Chernoff bound for random walks on expander graphs. And so we felt this containment is relatively easy, but the actual Chernoff bound for random walks on expander graphs is not so easy. So I mean, already here you'd expect something very straightforward for expanders. And I mean, maybe there is a nicer argument, but this already requires a good bit of work. So about these two conditions, these are sort of local conditions. So like trees and bounded degree allow you to work in somewhat locally. And this allows us to really get over one of the main difficulties of the problem, which I'll sketch here, is if we have a few loosely linked graphs, like this, well, after some linear number of steps, maybe like Cn over 2 steps, we expect to have covered a constant portion of the world. And we'd like to rule out the possibility that the rest of the graph is covered in the remaining steps. And it really could be that when your walk continues, it actually keeps entering the uncovered portions of the graph in places which allow it to cover quickly. So yeah, if each portion of the graph has uncovered places which are really uncovered, then the random walk will cover faster than you expect. And it's very difficult to control re-entry from one portion of the graph to the other portion of the graph. So you can sort of see in the case of trees how this re-entry is done. Since trees don't have cycles, we don't really have to worry about this. But already with bounded degree graphs, there are some issues. So I'll just sketch a very interesting lemma from BGM. And says is fix some bound on the maximum degree, and we'll study LVR is the number of visits to V before hovering. This is the ball of radius R around V. So here we acquire that all of BVR is covered. And then maybe the last vertex we cover is V, and we want the walk to continue out. And they prove that the expectation of LVR tends to infinity as R tends to infinity. And the amazing thing is this is even with adversarial reentry. Yeah, to BVR. So what I mean by this is when you're inside of BVR, the walk behaves like a simple random walk. But once you go to some vertex in the annulus and step out of BVR, the adversary is allowed to place you back into the ball at a place that really could speed up how quickly the walk covers. But even with this adversarial reentry, the expected number of visits to V still goes to, is unbounded. And like somehow they're taking this issue of reentry and they're saying, we don't care, we can deal with it even in the worst case of reentry. But it's really not clear how to deal with it.
It's also not clear why this is enough for an exponentially small probability.
Right, so this, I don't want to get into that too much, but this ends up powering a martingale bound. So using LVR, this really shows that some martingale has a large expectation. And it turns out that the sum of these things has bounded differences as well. I mean, appropriately defined. It's not, they're not quite studying LVR. But yeah, it powers a pretty surprising martingale argument. So, very nice result. Okay, so today.
But this body is unmovable. So if you want to, you can pull down the.
All right. Yeah, actually, that is probably. Yeah, thanks. So yeah, this will be the important slide. So I would want to keep this up. Yeah, so today I'll be presenting proof of the theorem. So this really says, I'll restate the conjecture so we have it somewhere. For any graph, the probability of linear cover time is exponentially unlike. All right, so yeah, so Jeff and I proved the conjecture, and the main result, which it follows from in some sense, is a general result for Markov chains. So we prove for any C, there exists epsilon and also delta, such that in a Markov chain, with transition probabilities bounded by delta, we have some linear cover time statement. Okay, so in Markov chains, you really do need this extra parameter, of course. I mean, there are very simple examples. If your state space is a cycle and you go to the right with probability 1/2 plus eta, and to the left with probability 1/2 minus eta, then really for any starting position, the walk is going to cover in a linear number of steps. But this is, it's pretty close to the deterministic Markov chain, which just cycles throughout the vertices. So we need some deterministic hypothesis, and transition probabilities bounded by a constant turns out to be enough.
So the application of this to theorem 1 means that you need a low bound of the degree.
Exactly. So yeah. So an immediate corollary from the Markov chain theorem is theorem 1 for somewhat large min degree.
After that, you can apply the BGM.
Yeah, except for not quite this. Yeah, so BGM needs all degrees bounded, and this corollary needs all degrees large. And there's somewhat of a gap between there. And it turns out the BGM result is relatively sensitive to even a couple large degrees. I mean, a couple being much larger than 2, of course. But yeah. So yeah, we immediately get this corollary, and this is interesting even in the case of the Hamming cube. So if our graph is the Hamming cube with natural adjacencies, we get the linear cover time statement from this corollary for the family of graphs of the Hamming cube. But really, we don't have a simple argument. So you might think with all this information, there's some nice argument that we can do something ad hoc. But yeah, this was a test case for us for a while, and we really had no luck there. So it'd be really nice to see something direct.
What if you replace every vertex by a small complete graph with like 1/delta vertices, and then like the random walk would be thought of as like a lazy random walk? Where you have, but still the probabilities are like delta, and that doesn't fix it. I don't know, just
yeah, I mean, the laziness is gonna push up the cover time. So I mean, the main one issue here is that delta,
like by factor delta, like that depends on that.
Yeah, so delta depends on C. So for us, if we want to blow up every vertex like this, the laziness is also going to make the cover time go up as well. And delta is going to grow, or 1/delta grows much faster than C. Yeah, yeah. Okay, yeah, so you might try and combine it with BGM, but yeah, we didn't have any luck there either. So really, we'll have to go a different route. And it'll turn out that theorem 1 will follow from the Markov chain theorem, but we'll need to do a bit more work and show how this Markov chain theorem applies for lower degrees. So the plan for the rest of the day is one, I'll outline how this works. And then the second thing is I'll sketch something about the Markov chain theorem. Okay. All right, so any questions on where we are now? All right. Okay, so the proof of theorem 1, as I said, is going to follow from the Markov chain theorem. And the issue again is when we have bounded degrees, the transition probabilities can be somewhat large. And we weren't able to prove anything stronger in terms of dependence of delta on C. So we'll need a way to lower the transition probabilities. And the way we'll do that is by passing to an induced Markov chain. So we have some subset of the vertices. And really, to sample from the induced chain, we'll sample from the original random walk, but we'll only record visits to W. So if we're at some vertex in W, the next vertex might also be in W, but it could leave W and meander about for a little bit before it enters. So this, of course, changes transition probabilities, and formally, we'll denote this by phi W. So these are transition probabilities on the induced chain on W. And the probability of transitioning from V to U is the probability that the next vertex in W after leaving V is equal to U. And this will be nice because sometimes passing to the induced chain smooths out transition probabilities. So a somewhat silly example is if the original graph is a star and we pass to the induced chain on the leaves, then this becomes the complete graph of leaves. So, and this is a somewhat extreme case in terms of the smoothing. But you can see the random walk, once it leaves some vertex, will step into the middle, and then the next step is uniform among the leaves. So really the next step, leaving some vertex, is uniform among all the vertices here. Also in the cube, for example, passing to the set of even and odd vertices smooths out transition probabilities. But taking a random set does not do as well. That's smoothing things out. So you need to be careful about passing to this. And in fact, passing to a smaller subset can, of course, increase the transition probabilities. So one needs to be very careful about doing that. But this will be the main point, is that there might be some way of smoothing things out. Okay, and when you do this, there are also some errors. So it's somewhat difficult to work with this. So we'll need a more robust version of the Markov chain theorem. And this says that for any C and now gamma, we can find our constants epsilon and delta, such that if in a Markov chain Xi, if there exists a subset of vertices with transition probabilities into W. Actually, let me look at this. Delta U. Then we have the linear cover time statement for the random walk on V. And really, we even have it for the random walk just looking at W.
What happens to gamma?
Sorry, what did you say?
What happens to gamma?
Gamma is, thank you, yeah. So we really need this to be in a linear number of steps. Yeah, thank you very much. Okay, so slightly more robust, and we really only need to work in a constant part of our world. All right, and the way we'll apply that is the following corollary. And it's a bit long to state, but the main idea is not so bad. So I'll give a picture after writing everything down. But we immediately get, now if you fix C, gamma, and theta, we can find epsilon delta.
What is the exact statement? What do you require about you? Do you want the transition probabilities as you define them like before, the induced transition probabilities to be delta?
Not yet. So these are actually really just the transition probabilities into U.
Okay.
Yeah. Actually, we can forbid loops. Loops can happen with high probabilities. So you could pass to some lazy chain as well. But we really just need transition probabilities into U. I mean, and the main picture here is that we need some vertices which you can't hit deterministically. So as long as going into U has enough randomness, we get our linear cover time statement.
Wait, can you define what is exactly transition probabilities into you? Like from who?
Yeah, so I really want that
In an undirected graph, the probability of getting out of it.
It's from every vertex in you.
it's just from every vertex in V. Yeah, I mean, we can forget about this, but this is not going to come up with us today. Well, more or less. Okay, so from this more robust theorem, we get that if there exists a partition of a large portion of the world, this partition needs to satisfy one, the union of the VIs make up constant fraction of the world. The second thing is each VI is somewhat large, so I. And thirdly, for every VI, there's UI contained inside of it so that it satisfies the hypotheses of this Markov chain theorem. And what this means is the induced chain on VI has bounded transition probabilities. So what this looks like is these are our VIs, 1, 2. And if you just look at some VI, then the induced chain on this part satisfies the hypotheses of this Markov chain theorem. And the proof of this is very simple. So proof of the corollary is if we cover the whole graph in a linear number of steps, then some VI is covered in C over. This is the. Thank you. Okay. Yeah. So if we cover in a linear number of steps, then some vertex is covered, or some vertex part is covered in a linear number of steps. Just because really this partition covers most of the vertices in our graph. And from the Markov chain theorem, this happens with exponentially small probability. And from the condition that each vertex part is linear size, we have that there are constant number of vertex parts, and we can take a union bound The probability that we cover in linear time is at most k. And yeah, this is just some constant, so we can take this. All right. So of course, now this leaves open the question of whether or not there exist partitions. So partitions. So we show there exists partitions, meaning vertex sets as in the corollary under a set of assumptions that I won't go into. Otherwise, we're done. So if these assumptions don't hold, really then we get the walk somehow moves very slowly, and we get the linear cover time statement for other reasons.
Why do you need a partition? And it's not enough to have just, if the subset is of linear size, why isn't it enough to have just one of them?
That would be enough, but it's, yeah, we didn't know how to find such a thing. So we had to pass to this partition. I mean, somehow, like the transition probabilities, I think should grow based on how small these vertex parts are. So it's helpful to have smaller things in the partition. But yeah, if you could find just one part satisfying the assumptions, then you would also be okay. Okay, so we say there exist partitions under some assumptions, and otherwise the linear cover time statement is true for other reasons and other easier reasons. So this completes the proof of or the sketch.
You should give us just a hint or intuition. But how do you find, or is it an existential statement? Is it an explicit algorithm?
Right. Yeah, so the main thing is the way we show these partitions are very much, it's not explicit at all. So we're looking at properties of the walk, and we're able to show that if the walk spreads quickly, meaning like leaving a vertex, the number of vertices you see in the first t steps is linear in t, then really it should spread out throughout the graph. And actually, so this ends up powering a random choice, but making this random choice and showing that it works is not so easy. So yeah, open question here is, do such partitions always exist? Yeah, so as I said, we had to work pretty hard to make the random choice work. And somehow, like even Aldous and Phil remark in their manuscript on reversible Markov chains and random walks on graphs that transition probabilities tend to spread out with respect to some intrinsic geometry. And it would be nice to find partitions that really get at the heart of that statement, because formalizing this seems to be very difficult.
Does the partition have any nature that, you know, in each part, it's sort of more expanding, and between parts, it's, as pure edges or unlikely to move between parts or not?
I'm not sure about the expansion probabilities, but really, I'm thinking of them like a code, so that like the vertices should be very far away.
So I guess the idea, so a natural idea to make degrees large is to take, an independent set of things that are otherwise far apart. Like
yeah, exactly.
So, but of course, depending on the graph, it can be.
Right. So yeah, and there are cases with vertices arbitrarily far apart where transition probabilities are still quite large, like even up to a half. But on expanders, for example, you can take vertices sufficiently far apart, and this gives you the partition that you want.
In fact, it will give you one set, which is probably good enough.
But it will be, Well, it actually would be still pretty large, but no, I think.
And like, I know if you take, code, like every pair is, 10 apart, or 1 over delta squared apart, don't you get this condition in the?
Yeah, you do get this condition, but I'm worried about if the size of this, like the distance you take is going to depend on C. And we're looking to get transition probabilities below some function of C. So again, we have this issue. And this is why we really need a partition as opposed to just one part. Okay, so, and that is now all I have to say about it. All right, so questions on the corollary? All right, so yeah, for the rest of the time, we're going to sketch this Markov chain theorem. And I'm only going to do this for regular graphs. So for the remainder of the talk, G is going to be a deregular graph, and D will be chosen later, very large. So set some parameters. K is going to be much bigger than C. And for convenience, we'll set P is. So this proof is very much inspired by result of Aldous, who proves that the expectation for reversible Markov chains under some suitable non-deterministic hypothesis is also n log n, at least n log n. And the things I'm defining now are somehow his. Well, first we have the hitting time of V is standard, but so that's the first visit to the time of the first visit to V. But RV is not standard. It's the time of the visit to the neighborhood of V. And then finally, the event QV is the event that we hit vertex V after visiting its neighborhood many times.
RV, what? I missed what RV is.
So RV is the time of the KDth visit to the neighborhood of a vertex V.
Anyone?
Yeah, so I'm defining random variables for each vertex V in the graph.
When you say visit to NV, you just mean to one of them.
Yeah. Yeah, so we'll have the vertex set, like for each vertex, we have a different random variable. And I'm just looking to define it, I'm just looking at that vertex set.
I think Tony just has to make sure that visit to NV means visit to any
Some
member of this set.
Oh, okay, yeah. So, yeah.
The D is, sorry, I lost track of D.
The degree.
Deregular, thank you.
Yeah, and to be determined.
Mhm.
Okay, so QV is the event that the walk hits this neighborhood many times before eventually hitting the vertex V. Okay, so letting Z be the set of vertices for which QV holds. Z is sort of set of vertices which are hard to hit by the random walk. So we had to work somewhat hard to hit these vertices. And we can do same thing with linearity of expectation to get that the expected value of Z is roughly n times probability of QV. And this is n. And choosing D large, this is essentially Tn. Okay, so we have a linear number of vertices which are hard to reach. And moreover, using a Zuma-Hofting inequality and defining some martingale capturing Z, we have the probability that Z is far from its expectation is exponentially small. And actually, this concentration result holds for the entire walk, so not just in the first CN steps of the walk. So really with all but exponentially small probability, there is some set Z which is pretty large. So just for making things easy, I'll be assuming that Z is bigger than Pn this whole time. So
Well, I thought at some point it's sorry. So this definition does not depend on the time it takes the walk.
no, so
It does not depend on the time.
it doesn't depend on the time. So the first iteration of the argument did have Z depending on the first number of steps, but using slightly stronger martingale argument, which Jeff introduced in his paper about list coloring graphs, you can show that Z actually is concentrated throughout the whole walk. So you will have somewhat large differences, or like constant size differences in the beginning of the walk, but these differences won't be large for the entirety of the walk. So in fact, we will get this linear concentration. And what this says is the walk doesn't meander about too much and get lucky hitting the graph like this. There's some core vertices which are difficult to hit. So the remainder of the proof is showing that in the first CN steps, Z won't be fully defined with all but exponentially small probability. Okay, so first thing is a lemma.
So if we define the walk the walk will define Z.
Yeah.
I mean, it is well defined in advance.
Yeah, it's defined, meaning that
You could identify a subset of a large subset of Z from the walk.
right. So yeah, what I mean is that in the first CN steps, we won't have this many vertices whose neighborhood have been visited KD times.
Oh, it just will be missing vertices, but when it's not clear the fact that they are missing has any relation to this property QV.
Yeah, missing is a bad word. I shouldn't. Yeah, I use that in terms of hitting. But really, what I mean is that to enter into Z, you have to have your neighborhood visited KD times, and this actually is rare. So usually, most vertices will have their neighborhood visited CD times in the first CN steps. So really, it's rare to have a linear number of vertices whose neighborhood have been visited that many times.
So the
idea
there in picking the value of P is that picking the value of K.
Yeah.
Why?
Just like, so you will have not exponential. We just have KD type. So you get KD chances of seeing V and you miss them all.
Yeah.
Each with probability. So it's exponential in K.
Mm-hmm.
Oh.
Yeah.
But why wouldn't you need to argue? I mean, another way to know that a vertex is not in Z if you just visited it before you visited its neighborhood many times, right? So you also need to argue something like, I haven't visited all vertices in the first CN steps because otherwise also Z is defined.
Yeah, but this is what this concentration is doing. So we know that there are vertices which are hard to hit with all but exponentially small probability in any random walk. So we can really, since we're just trying to prove some exponential bound, we can assume there are a lot of vertices that have been hit. So we're working under the hypothesis that we cover in linear time, which means under this assumption, there are a bunch of vertices that were hard to hit, and we visited their neighborhood KD times before covering. Okay, so first limit to get close to that is for some subset of vertices. QI be the event that QV holds for every vertex in the pattern. And we have some negative correlation result. Probability QI is at most the product of the probabilities of QV. Yeah, which is at most p to the I. This is somewhat natural because if two vertices are both hard to hit, that if they share some vertices in their neighborhood, it somehow forces if V and W are both hard to hit, then when you're at this vertex, not stepping to V means it's more likely to transition to W. So we have some negative correlation result, and this is pretty strong result because we may assume that I is linear size. So immediately we can try out something like this. We know there exists some I with I bigger than Pn, such that Qi happens. So under this assumption that Z is large, so we get something like probability that we cover in linear time is the most number of possibilities for I times the probability that Qi holds. And this ends up being no good. I mean, this is like binomial calculation. And also we haven't used the fact that we covered the walk in linear time. Because again, we have this concentration for Z without that assumption. So we need to do more. And what we'll do is showing that actually we can make a union bound work. So the main point is that Z has structure. How am I doing on time?
You have 10 minutes or so, more.
No, that should be.
So just to make sure, I mean, the I's are really zero subsets of the large subset of the in principle. So or what would be Z?
Yeah, so I is going to be some subset of Z.
Yeah, so saying having it has some structure, meaning this is a union bound, you take it over sets with structure, which will be much pure.
Exactly, yeah. Okay, so Z has structure, and the main point of this is that if a vertex is in Z, then Cn is bigger than the hitting time of V, since we cover every vertex, and this is bigger than RV. And this event that RV happens in the first Cn steps is the rare event that we'll be working with. Okay, so we have the lemma. If Z is large, then yeah, and we cover in linear time. Then, well, the first thing is there exists some set of vertices y prime, such that, first of all, y prime is not too big. It's like Cn over Kd. And secondly, the neighborhood of y prime has a large intersection with Z. So what is happening is we have our linear size subset Z, and because for every vertex in Z, we spent a lot of time in the neighborhood, it actually means that we can find a very small set of vertices Y prime, which has a big intersection with Z. And so essentially the reason that we've visited every vertex's neighborhood in CN steps is because we spent a lot of time in Y prime. And what we'll do is we'll take I as the neighborhood of Y prime intersect with Z. Okay, so we'll take I equal to the neighborhood of Y prime intersects.
And then the union bound will be over only set Y prime.
Right, so yeah, we can take a union bound over such sets. Because we know that Z is large and it has this very specific structure. So letting n be number of possibilities. We have to choose I, we get the first thing is you choose some Y prime over all possible subsets of this size. And then you choose I in the neighborhood. Choose P over 2n. Okay, so we find that n is at most, and choose Cn over Kd times Cn over K, choose P over 2n. And now we see where the large degree condition comes in, because we can choose D large to make this first factor small. And we can choose K large to make the second factor small. So making these choices appropriately, we get something like 1 over 5p to the Pn over 2. All right, so finally, to make the union bound go, we have probability is at most number of choices for I times the probability Qi holds. And this is going to be all right, so yeah, that's the end of the proof, and is all I wanted to say for today.
Thanks a lot. Questions? I think it has to be some complicated, or that there is some slicker proof somewhere.
I'm not, I mean, this proof is not so bad. And maybe you could extend it. Like this Markov chain proof to cover all cases. But yeah, I don't know. We tried for a good amount of time, so yeah, all I can say there.
You mentioned something about that this was based on this result of algebra. But can you explain more what that result was and how it relates? What exactly is related?
Yeah, so all this proves for reversible Markov chains satisfying non-deterministic hypothesis, which is actually a bit weaker than ours. that the expected cover time is at least a constant times n log n.
It's not about the probability of.
I see.
Yeah, so still working with the expectation.
You said that the definition there of
It was,
This
yeah, that's what
nevertheless,
the definition. Oh, I see. So that's what was
yeah.
related, not the result. It was the RV.
Yeah, so the argument is like an adaptation of his, and really studying like the number of visits to a vertices neighborhood is his. Although KD is something else for him. It's much larger.
What's that hypothesis? That non-deterministic? It's hard to describe. It's okay.
Yeah, it's not so easy. I think he says some parts can be replaced with just a bound on the transition probabilities. But yeah, his bounds are certainly weaker. His assumptions are definitely weaker in a lot of ways. And maybe this result would extend to those cases, but for our result, weren't very useful. So.
Why do you need both K and D large?
So we need D large just to make this the first factor small, and then this still can be quite large. If K is just C, then this factor is going to.
If K is very large, isn't the first factor also small?
Yeah, if K is large, we need the first factor small, but you need it to be very small. So you need to be smaller, like compared to like Pn or something like that. So yeah, how to explain this? Really, just taking without this D factor, you run into some issues. I don't know how to explain
e
it.
to the minus k is
Yeah.
b, so you need something else to lower it.
So like you need K to be K is a constant, right? B is not a constant.
Yeah, so you can take K like 1,000 times C or something like that.
Yes.
Yeah, and
I mean, D would need something that is more than a constant.
yeah, so D should be something like e to the K, something like that is enough. Maybe.
I see. No, I thought it needed to be something that depends on n.
Yeah, no, yeah, this is okay.
A very historical comment. If anybody was wondering why so many, besides combinatorialists and probabilists, why so many computer scientists were obsessed with the cover time in the 80s and 90s. So in 1980, Karp, Lovaas, Lipton, two others that I don't remember,
Rakoff and Rakoff.
yeah, they proved a relatively simple result that that was mentioned before, that a random walk will cover any undirected graph of size n in polynomial time in n, which means that you can solve the just undirected connectivity problem in logarithmic space if you have coins. And then everybody was interested in de-randomizing it. I mean, can you solve connectivity in log space? But I mean, it just drove a lot of interest in the cover time of random walks, and yeah, it was a huge industry at that time. Yeah, of course, it took about 25 years till Omer Reingold de-randomized that random walk. And all right, more questions. Thanks.